In physics, escape velocity is the speed at which the kinetic energy plus the gravitational potential energy of an object is zero. It is the speed needed to break free from the gravitational attraction of a massive body, without further propulsion, that is, without spending more fuel. For a spherically symmetric body, the escape velocity at a given distance is calculated by the formula, where g is the universal gravitational constant, m the mass of the planet, star or other body, and a the distance from the center of gravity. In this equation, atmospheric friction is not taken into account. A rocket moving out of a gravity well does not actually need to attain escape velocity to do so, but could achieve the same result at any speed with a suitable mode of propulsion and sufficient fuel. Escape velocity only applies to ballistic trajectories. The term escape velocity is actually a misnomer, and it is often more accurately referred to as escape speed, since the necessary speed is a scalar quantity which is independent of direction. Overview. A barycentric velocity is a velocity of one body relative to the center of mass of a system of bodies. A relative velocity is the velocity of one body with respect to another. Relative escape velocity is defined only in systems with two bodies. For systems of two bodies, the term escape velocity is ambiguous, but it is usually intended to mean the barycentric escape velocity of the less massive body. In gravitational fields, escape velocity refers to the escape velocity of zero-mass test particles relative to the barycenter of the masses generating the field. The existence of escape velocity is a consequence of conservation of energy. For an object with a given total energy, which is moving subject to conservative forces, it is only possible for the object to reach combinations of places and speeds which have that total energy. And places which have a higher potential energy than this cannot be reached at all. For a given gravitational potential energy at a given position, the escape velocity is the minimum speed an object without propulsion needs to be able to escape from the gravity. For the sake of simplicity, unless stated otherwise, we will assume that an object is attempting to escape from a uniform spherical planet by moving directly away from it, and that the only significant force acting on the moving object is the planet's gravity. Escape velocity is actually a speed because it does not specify a direction. No matter what the direction of travel is, the object can escape the gravitational field. The simplest way of deriving the formula for escape velocity is to use conservation of energy. Imagine that a spaceship of mass m is at a distance r from the center of mass of the planet, whose mass is m. Its initial speed is equal to its escape velocity. At its final state, it will be an infinite distance away from the planet, and its speed will be negligibly small and assumed to be zero. Kinetic energy K and gravitational potential energy UG are the only types of energy that we will deal with, so by the conservation of energy, K equals 0 because final velocity is 0, and UG equals 0 because its final distance is infinity, so. Defined a little more formally, escape velocity is the initial speed required to go from an initial point in a gravitational potential field to infinity with a residual velocity of 0, with all speeds and velocities measured with respect to the field. Additionally, the escape velocity at a point in space is equal to the speed that an object would have if it started at rest from an infinite distance and was pulled by gravity to that point. In common usage, the initial point is on the surface of a planet or moon. On the surface of the Earth, the escape velocity is about 11.2 km per second, which is approximately 33 times the speed of sound and several times the muzzle velocity of a rifle bullet. However, at 9,000 km altitude in space, it is slightly less than 7.1 km per second. The escape velocity relative to the surface of a rotating body depends on direction in which the escaping body travels. For example, as the Earth's rotational velocity is 465 ams at the equator, a rocket launched tangentially from the Earth's equator to the east requires an initial velocity of about 10.735 km per second relative to Earth to escape, whereas a rocket launched tangentially from the Earth's equator to the west requires an initial velocity of about 11.665 km per second relative to Earth. The surface velocity decreases with the cosine of the geographic latitude, so space launch facilities are often located as close to the equator as feasible, for example the American Cape Canaveral and the French Guiana Space Center. the barycentric escape velocity is independent of the mass of the escaping object. It does not matter if the mass is 1 kg or 1000 kg, what differs is the amount of energy required. For an object of mass, the energy required to escape the Earth's gravitational field is gmma/ar, a function of the object's mass. For a mass equal to a Saturn V rocket, the escape velocity relative to the launch pad is 253.5 ms faster than the escape velocity relative to the mutual center of mass. When the mass reaches the Andromeda Galaxy, the Earth will have recoiled 500 m. Orbit. If an object attains escape velocity, but is not directed straight away from the planet, then it will follow a curved path. Although this path does not form a closed shape, it is still considered an orbit. Assuming that gravity is the only significant force in the system, this object's speed at any point in the orbit will be equal to the escape velocity at that point. The shape of the orbit will be a parabola whose focus is located at the center of mass of the planet. An actual escape requires a course with an orbit that does not intersect with the planet, or its atmosphere, since this would cause the object to crash. When moving away from the source, this path is called an escape orbit. Escape orbits are known as C3 = 0 orbits. C3 is the characteristic energy, equals a gram per hour, where a is the semi-major axis, which is infinite for parabolic orbits. When there are many gravitating bodies, such as in the Solar System, a rocket that travels at escape velocity from one body, say Earth, will not travel to an infinite distance because it needs an even higher speed to escape the Sun's gravity. Near the Earth, the rocket's orbit will appear parabolic, but will become an ellipse around the Sun, except when it is perturbed by the Earth, whose orbit it must still intersect, and other bodies. List of escape velocities. Because of the atmosphere, it is not useful and hardly possible to give an object near the surface of the Earth a speed of 11.2 km per second, as these speeds are too far in the hypersonic regime for most practical propulsion systems and would cause most objects to burn up due to aerodynamic heating or be torn apart by atmospheric drag. For an actual escape orbit, a spacecraft is first placed in low Earth orbit and then accelerated to the escape velocity at that altitude, which is a little less about 10.9 km per second. The required change in speed, however, is far less because from a low Earth orbit the spacecraft already has a speed of approximately 8 km per second. Calculating an escape velocity, to expand upon the derivation given in the overview. Where is the barycentric escape velocity? G is the gravitational constant, m is the mass of the body being escaped from, r is the distance between the center of the body and the point at which escape velocity is being calculated, g is the gravitational acceleration at the distance, and I1/4 is the standard gravitational parameter. The escape velocity at a given height is times the speed in a circular orbit at the same height. This corresponds to the fact that the potential energy with respect to infinity of an object in such an orbit is -2 times its kinetic energy, while to escape the sum of potential and kinetic energy needs to be at least 0. The velocity corresponding to the circular orbit is sometimes called the first cosmic velocity, whereas in this context the escape velocity is referred to as the second cosmic velocity. For a body with a spherically symmetric distribution of mass, the barycentric escape velocity from the surface is approximately 2.364 a, 10^5 m 1.5 ga 0.5 za 1 times the radius a times the square root of the average density I, or deriving escape velocity using calculus. Let g be the gravitational constant and let m be the mass of the Earth and m be the mass of the escaping body or projectile. At a distance of from the center of gravitation, the body feels an attractive force. The work needed to move the body over a small distance drive against this force is therefore given by the total work needed to move the body from the surface ρ of the gravitating body to infinity is then. This is the minimal required kinetic energy to be able to reach infinity, so the escape velocity VO satisfies. Which results in multiple sources. The escape velocity from a position in a field with multiple sources at rest with respect to each other is derived from the total potential energy per kg at that position, relative to infinity. The potential energies for all sources can simply be added. For the escape velocity, it can be shown that this gives an escape velocity which is equal to the square root of the sum of the squares of the individual escape velocities due to each source. For example, at the Earth's surface the escape velocity for the combination Earth and Sun would be. See also orbital speed, characteristic energy, delta V budget a speed needed to perform maneuvers. Gravitational slingshot a technique for changing trajectory. Gravity well, two-body problem, black hole an object with an escape velocity greater than the speed of light, or birth effect burning fuel deep in a gravity field gives higher change in velocity. Newton's cannonball, list of artificial objects escaping from the solar system, list of artificial objects in heliocentric orbit, notes, the gravitational potential energy is negative since gravity is an attractive force and the potential energy has been defined for this purpose to be zero at infinite distance from the center of gravity. The value gm is called the standard gravitational parameter, or I1/4, and is often known more accurately than either g or m separately. References: Roger Abate, Donald D. Muir, and Jerry E. White. Fundamentals of Astrodynamics. New York, Dover Publications. ISBN A0-486-60061-0A. External links: web-based numerical escape velocity calculator.